Okay, we are live. Hi. Today is going to be a bit of an extravaganza. We are going to go down a large rabbit hole, but only for one day. And the goal is to see if generally anything in model-based just works and is easy, or if it seems like that's just not the case. There are a couple papers that I definitely want to look at. This is sketchy. This should not have failed. That must have just like broken. We are going to check the nighttime runs, though, the runs from last night, real quick. So I believe this was, yeah, this is the recent one. Interesting. Well, we will see how this turns out. I don't like this intersection, but it is training. Okay. That's all we had to check. Just make sure that it has not catastrophically failed. Train curves are generally fine. So a few papers I want to start with. I haven't looked at this in a long time. I do not like this paper one bit because, well, half of it's wrong. But we will look at the core world model. I think these are probably the two that we should look at. Yeah, okay. We'll start with this. It's been several years since I've read this. I remember liking this paper. Let me see how they do their world model. We'll go to paper mode. How mu0 uses its model to plan. Given previous hidden states and a candidate action, the dynamics G provides an immediate reward R and a new hidden state SK. Policy and value are computed from the hidden states by predicting a function f. The initial hidden state S0 is obtained by passing the past observation into a representation function h. Okay. So this could just be multiple heads on the same network, right? You have your LSTM or whatever producing states. You predict reward. Policy value. Okay. Here's their algorithm. Predictions are made at each time step t for k0 to uppercase k. Is that a k? I think it is. By model mu of theta with parameters theta conditioned on past observations. What's on the docket today? Is it the Atari 2-week paper? No, that's awful. That is off policy. We're going to look at model-based stuff today. I think is going to be more promising. If you want to use a crap ton of compute to do something, I think that the off policy stuff is kind of just not the way to do it compared to this. So we're basically going to try to see if anything model-based makes sense today and like immediately helps. The ideal is to, let me just sort of outline my goal for today. I would like PufferLib to be, to have a core algorithm that can be very, very fast if you have infinite data, but also you can kind of just turn the knob and use more compute on the same data. And the thing that in my mind makes the most sense for that is a certain form of world model based, specifically something like this that's kind of similar to learned search. Compression and search are the two things that we know scale. So this is kind of both. The model predicts 3 future quantities. Okay, the policy, the value function, and the immediate reward. Internally, at each time step, the model is represented. It's got to predict next obs, doesn't it? Model is represented by the combination of a representation function, a dynamics function, and a prediction function. The dynamic function that computes at each hypothetical step k an immediate reward in an internal state s. Okay, so this is going to predict, this predicts next state as well, which is what we'd expect. But it predicts internal state, not obs, which is very nice. Unlike traditional approaches to model-based RL, this internal state SK has no semantics of environment state attached to it. It is simply the hidden state of the overall model, and its sole purpose is to accurately predict relevant future quantities, policy, value, and reward. Okay. In this paper, dynamics functions represented deterministically. Prediction function F computes the policy and value function from internal states, SK, BK, VK, akin to the joint policy and value network of alpha 0. A representation function H theta initializes the root state S0 by encoding past observations. This has no special semantics beyond its support for future predictions. Given such a model, it is possible to search over hypothetical future trajectories A1 through OK, given past observations O1 through OT. For example, a naive search could simply select the k-step action sequence that maximizes the minimum value function, yes. More generally, we may apply any MDP planning algorithm to the internal rewards in state space induced by the dynamics function. Specifically, we use an MCTS algorithm similar to AlphaZero search, generalized to allow for single agent domains and intermediate rewards. All parameters of the model are trained jointly to accurately match the policy value and reward predictions. For every hypothetical step k, to 3 corresponding targets observed after k actual time steps have elapsed. So you only get to train this on the You only get to train this on the action that you actually take, right? Which is fine. Value targets are generated by playing out the game, or MTP, using the search policy. Unlike AlphaZero, we allow for long episodes with discounting and intermediate rewards by computing n-step return that bootstraps n-steps into the future from search value. Yeah, okay. I remember really liking this paper, and I still really like this paper. This is just like a very clean way of doing MCTS without access to dynamics. And we literally have Go to try this on if we wanted to. And then this does ludicrously well on Atari as well, which makes sense. Okay, so I see how this works. Dreamer only claims to be better on... This claims to be better on Atari, and it claims to be better on Minecraft. But this algorithm is a total fucking mess, so... Yeah, this is a full encoder-decoder. This is an RSSM. Is there any difference between this and Mu0 except for the fact that they use an RSSM and then they use they predict output obs instead of hidden states? Let's see how big their policy is. So one of the papers uses world models to model trajectories tens of steps into the future. I mean, it depends on the environment whether you can do that, right? But like, you absolutely should be able to do that with something like Go. It's like very obviously deterministic. In like a very easy to predict way, right? Do they have the policy size? Let's have some search algorithm to pick and refine steps instead of just an action policy. So my understanding of this, and I just have skimmed this and I read this years ago, right, is that you're training a world model, which is, in this case, you're just predicting the next hidden state dynamics, and then from that you're predicting reward and action, right? And then you run MCTS over that in order to predict the trajectory that you actually take, and then you backprop on that. They use it for continuous control. So this is fully general. You can use this on any problem type. I don't know how far forward you can prop on continuous control. The thing with tens of steps in continuous control is that can actually be a very small window of time, right? Like 10 steps in Go is actually a lot of stuff happens. 10 steps of robotics is not very much happened. So I go by like real-time equivalence. Okay, they have the architecture here. They have 16 residual blocks. That's got to be way smaller than 200 million parameters, right? Quantization, it was a couple of seconds. Okay. Even if they picked a trajectory, they pick the first action, then rinse and repeat. Figure out a new trajectory after one step. Yes. Yeah, that's what you would expect. So the thing is then you're only really training on are they training on the whole trajectory? They're not then, right? You only get to train on the data that you actually see, which is the action that you actually take, right? So you generate a whole bunch of these rollouts, but you only get to actually see the result of one action. Then learn on regular rollouts. It's normal, do replays. So that seems very clean to me. I think the Dreamer is kind of just, they did the same thing, except they do a decoder for the actual, like they decode and predict the full image or whatever instead of predicting state, which is actually a bad thing because it makes it really obnoxious to do partially observed state type environments because like you have to write an obnoxious inverse encoder to decode. And then they have like RSSM or whatever. This is not like that meaningfully different from U0, right? I also don't like autoencoders for that. Yeah, it's a real pain in RL. Let's ask Brock. Just in case. Sometimes it catches things, usually not. Mu0 I've missed. I'm washed. Mu0 was the good one, I think. I remember I liked that paper reading, and I don't like most of the world model papers. Also, Dreamer v3 is like half wrong, so. Okay, this doesn't use MCTS. Oh yeah, okay, I remember. So they train on imagined rollouts. Right. There's a big difference here. Embedding is good if you can train inverse. Yeah, it's just that in practice, the inverse world models are really obnoxious to define, right? Okay, so I think that I see mostly how this works. I think it makes sense to spend a little bit more time making sure I understand the details fully here. So what we would do here, we would add like some additional network head that probably actually has to have a couple layers on it, right? Um, and that will predict. Or we could just have, should it just be another LSTM? It could just be another LSTM, right? Hang on, how do we roll this thing forward reasonably? It has to be conditioned on the actions, right? Versus this thing. You just train everything on imagined rollouts. See, the thing that's sketchy about this paper, right, is it depends on all these tricks that we know don't actually work. What about wall time? So the wall time of this model is evidently actually quite good. The thing that's sketchy about this is, so this goes up to a 200 mil per am model. Um, and it's like the perf is very highly dependent on all these tricks, like half of the perf. But these tricks are absolute bullshit. Like we've tested them, we have a NeurIPS paper on it, they're bullshit. So it's a very like sketchy thing to get to work. It's also kind of like an all-in algorithm in the sense that like when you're actually training on the world model itself, it has to be really good. Um, I think that mu0 is a better fit for what we're looking for at the moment, which is like, I think with this, you can kind of just do your on-policy learning the way that you normally do, right? And then like you can scale up. You can scale up if you want to, like scale up compute to do more search to get better data. This also gives you test time scaling for free, doesn't it? Yeah, this gives you test time scaling for free, which you would think would mean you'd also be able to use a much smaller model. And like with these residual blocks, it seems like this would be smaller as well. Okay, let me make sure I actually figure out how this is implemented. Where's the algorithm? IRL row bottoms, then it has a modicum of sense. I just want something where we can crank up compute if we want, right? Without screwing up our base algorithm. So this seems like we can just train this auxiliary thing and then use that to crank compute when we want to. I wish they had an algorithm block on this. Let me see if I can draw this out, and then we can try to maybe implement this. So like, here's your normal RNN, right? And this is also V1. So they predict reward now directly. So this is gonna get R1, I guess. Or do we not need to? Hang on. We need some way to encode. I think you need to encode both the action and the state, right? I think it's like action state pair has got to be the input. Let's see where they describe this. Oh, they have this as well. These on. I think it's just you add an extra model, right? How do you get the actions? Okay, so unrolling this is actually kind of tricky, right? Because you sample the action. Let me just read this full thing. Model just models aspects that are important to agent decisions. How good is the current position? What action to take? Reward. How good was the last action? But then it needs the state model, right? Yeah, the dynamics function. which does take the action. Okay. So the only obnoxious thing about this, right, is this has to be an LSTM cell, not an LSTM, I believe. This scales up inference time compute, doesn't it? Because you do this in the data collection phase. I know I had asked you this question last night regarding last up first desktop. How did you get comfortable with Linux daily coming from Windows? If I recall, I've used Linux forever. WSL2 is basically native Linux. Um, it's just required. If you're doing anything in scientific computing or really even programming in general, you're just using Linux, and you're really just like limiting yourself otherwise. Like outside of .NET, like Windows is just not a serious development environment. .NET and game engines, I guess. That's about it. So if we do this as an LSTM state, right? Then we can write a pretty basic piece of code. So it's like A, and this is like actually this is S1, isn't it? Or do you do your own embedding of obs? Could be either. So you do this, and then this will produce. Well, this doesn't produce O. Oh, I guess this is what this is supposed to be. This is like E1 or whatever. And like you look right here, this is E1, right? And then this is gonna produce E2, right? And this will probably also produce some other stuff. No, it just produces E2, I guess. But then what about S? Thank you for response. Contemplating full Linux desktop. You don't have to immediately like go buy a new machine or something. You can dual boot, which is admittedly a bit of a pain in the ass, but it works. If you're on Windows, just use WSL because it's basically native Linux. It's the same dev environment and everything. It's like a really good option. Mac, a lot of people in industry use Mac. I frankly hate it, but it's like closer because it's a Unix environment. Not everything works the same, and there's a bunch of setup pain in the ass. Um, I myself, I have native Linux machines because it's easier. The other thing that you can do, which is another thing people will do, is they'll get themselves like a Linux box that they'll just SSH into or whatever to use for development, and then they'll access it from whatever they prefer to use. Just any of those is reasonable. Okay, so I think that this wasn't intended to be for an LSTM based model, right? Because you'd also have to predict this state, don't you? Or do you not have to? You have to predict the input state to this thing, don't you? Because if I roll this out, yeah, I can use this state. But then if I roll it out again, yeah, this state is now stale. So I have to predict the state as well. I mean, that's not terrible, right? Well, this thing is actually pretty easy to train, right? Because, like, you just train this on the actions of the trajectory that you actually took, the embeddings of the trajectory that you just took, right? And then the next one, the next, like, embedding. So that's not bad. This thing should be pretty easy to set up training for. You kind of want to give this the state as well, don't you? Oh, maybe what you do is you take these two and you put these in here, and then this is here, and then E2 is out. Yeah, okay, so it's actually, if I revise this, then what it should look like is this. It's just an LSTM cell that takes, this is E1, A1. This is S0, this is S1. And then this is E1 or E2. Now, can you train this like this though? I mean, this has to go into the main network now, right? This S1. Because then you have to put E2 and S1 into your net, which is fine, maybe? Maybe that's fine. It should learn the same representation. Wait a second. So if this is gonna get, can you not just put the previous action into this thing? Can this not just be one network? What if I just put like A0, A1 into these, and then this is going to predict E1? Does that just work? Because then I can use E1 instead of O as many times as I want, right? And it's a good idea to have the action in the input anyways. I was going to have to solve that problem. So then this literally just adds one head to the output. And then that lets you roll the model forward, right? And then the only thing that you have to do is you train this embedding versus this embedding. This also has to predict R now, right? Because you need that to know which one to pick. But I think that actually could be pretty simple. I don't even think you have to add like an extra network, right? You just have to predict E1 off of this. It's like a 2-layer MLP. That seems like it could work. So they said that there was a thing where they use more train time compute, though. Not just more inference compute, right? Let me read this more carefully. I'm just going to go through this out loud. We now describe mu0 algorithm in more detail. Predictions are made at each time step t, k0 to k, by a model mu pi theta with parameters theta conditioned on past observations O1 through OT, and for k greater than 0 on future actions at plus 1 through at plus k. The model predicts 3 future quantities. The policy pi of at plus k plus 1 conditioned on O1 through OT, comma at plus 1 through at plus k. The value functions vtk, which is equal to the expectation of some discounted return. This is just discounted return. And the immediate reward rtk equal mu tk plus t plus k, where u is the true observed reward, as a policy used to select real actions, and this is gamma. There's a discount factor. It's got to be. Internally, at each time step, the model is represented by the combination of a representation function, a dynamics function, and a prediction function. The dynamics function, g of theta, is a recurrent process. Represented. Okay. RK SK equals G theta SK minus 1 AK that computes at each hypothetical step K an immediate reward and an internal state SK. Does this mean it's a separate dynamics? Like it's a separate recurrent process? It mirrors the structure of an MDP model that computes the expected reward and state transitions for a given state in action. However, unlike traditional approaches to model-based RL, this internal state, SK, has no semantics of environment state attached to it. It is simply the hidden state of the overall model, and its sole purpose is to accurately predict relevant future quantities, policies, values, and rewards. In this paper, the dynamics function is represented deterministically. The extension to stochastic transitions is left for future work. A prediction function f theta computes the policy and value functions from the internal states. SK, PK, VK, f theta of SK, akin to the joint policy and value network of alpha 0. Representation function h of theta initializes the root state S0 by encoding past observations. This has no special semantics beyond its support for future predictions. Okay, so they're doing something a little different here. It looks like the policy is not a recurrent function, but the dynamics function is, potentially. But how does this work? So they take the initial state there are probably several ways you could implement this. Given such a model, it is, hang on, it mirrors, let's see, G theta is a recurrent process, RK-SK equals G theta SK minus 1 AK that computes at each hypothetical step K an immediate reward RK and an internal state SK. It mirrors the structure of an MDP model that computes the expected reward and state transition for a given state in action. However, unlike traditional approaches to model-based RL, this internal state SK has no semantics of environment state attached to it. It is simply the hidden state of the overall model, and its sole purpose is to accurately produce relevant future quantities. Okay, so this is not an encoder. This is not like an autoencode thing. In this paper, the dynamics function is represented deterministically. That's fine. A prediction function f theta computes the policy and value functions from the internal states akin to the joint policy and value function network of alpha 0. Oh, okay, so I have this wrong then. So it's not the same shared network. It's, so you have your normal net doing its thing, right? This is A1, 2, 3. And then this new model, it probably starts with observation or something. Double check. Representation function initializes the root state by encoding past observations. So we can probably just use this embedding here, right? So this can be S hat or whatever, and then we make a new dynamics function, which is another LSTM. So this is and this has to predict action does it need value? I mean, the simplest version of this would just be action and this just predicts action and reward. A1 R1 and now this has to take in does this make sense to have this here? Oh. This only has one input, doesn't it? I guess it gets the embedding of A. So yeah, so this has to get like these have to get rolled ahead. So this is actually like 2. Hang on. Oh, there's just no action in this one, I guess. Okay, so regardless, this starts to get like right? So you just have this separate network, and this one's going to just be similarly like the LSTM that we have, right? A little simpler even, because it's just the LSTM. Make sure I have this correct. Given such a model, it's possible to search over hypothetical future trajectories A1 through AK, given past observations O1 through OT. For example, a naive search could simply select the k-step action sequence that maximizes the value function. More generally, we may apply any MDP planning algorithm to the internal rewards in state space induced by the dynamics function. Specifically, we use an MCTS algorithm similar to AlphaZero search, generalized to allow for single agent domains and intermediate rewards. The MCTS algorithm may be viewed as a search policy and search value function VT, so expectation mu t plus 1, yada yada, that selects both an action and predicts cumulative reward given past observations. At each internal node, it makes use of the policy value function reward estimate to produce, combines these values to using look-ahead search to produce an improved policy pi, an improved value function v at the root of the search tree. What? Wait. Improved policy. Improved value function. Okay. All parameters of the model are trained jointly to accurately match the policy value function and reward prediction for every hypothetical step k to 3 corresponding targets observed after k actual time steps have elapsed. The first objective is to minimize the error between the actions predicted by the policy and by the search policy. Also, like AlphaZero, value targets are generated by playing out the game or MDP using the search policy. However, unlike AlphaZero, we allow for long episodes. It's fine. Second objective is to minimize error between the value function and the value target. Third objective is to minimize error between the predicted immediate reward and observed immediate reward. Okay. It looks ahead k equals 5 hypothetical steps. Hey, Cash. Doing well. We're doing model-based RL stuff today. Okay, so whatever. They have a fancy-ass tree thing. So the one thing I didn't get from the blog post was, where's this? Museo can repeatedly use its learned model to improve planning. Yeah, that's fine. Oh, so this is interesting, right? It actually does bootstrap itself. I don't see how this works. Mu0 reanalyze. They have this as this does worse. Okay, we can potentially ignore that. Oh no, because it's 200 mil. But that is a variant. So I think that we can kind of start with just like get a dynamics model, use it, see if it does anything, right? Yeah, I think we can start with something like this. This we can definitely implement today. The other stuff is like, it's going to be tricky to figure out how to make that stuff fast. This is like, I think we can do this batched, right? We should be able to do this batched, which should be pretty easy. Yeah, okay. I think we just got to start coding this. I think I've got like enough of an idea on how to like get started, and we got to start on this because this is going to be pretty substantial, and I want to make sure that we get the best chance we can at actually getting it to work today. Because I only really want to allocate today to seeing if model base does anything. I was messing with a bunch of stuff here, right? Yeah. Easiest way to start on this is going to be, does this get added to the LSTM wrapper? No, it doesn't, right? This does need to be a separate model, I believe. You can just put it in the top for now. And this needs to be LSTM cell, right? This kind of needs to be both, okay. We need to steal the trick that we did from here, which is like this. Put size, hidden size. Okay, so that gives us the LSTM. Action embedding works. And then you need an action proj and a reward proj. Like this. Let me move this out of the way. That's really it. So this takes in action, I believe, is all it takes. And then we can actually do the whole search inside of this now that I'm thinking about it, right? We could do the whole search inside this function. Let me code this for now. So here, you teacher force it, right? So it's literally then just going to be like super dot forward. Yeah, super forward. And then, yeah, and the state is just the input state, so this is totally fine. And then this gives you logits and reward. And then you train this thing with the actual logic and the actual reward. Okay, that's actually pretty easy. That's pretty easy. Should this technically work with, I think that this actually technically should work like this even. Like this should not crash training. And then what you do here is you add the loop here, which is your like search, whatever search algorithm. It just runs over this. I think that's how it would work. Yeah, that's how it would work. So I think that this is pretty much the only code you need with this. I could add the sampling into here to make it a little easier. Like this. You don't need to even know the reward here, so it's just action, log prob. I think you only need to know action from this. Okay. So then we do like something like this. Okay, and so now you have your policy here, which is computing logits and values. And you need to give it needs the embeddings, doesn't it? It needs like the initial embedding? Or what does it need? Yeah, it needs the initial embedding of observation to have the first state, I guess. You could technically learn this. You could technically learn this, but I think it would be harder. Because you're only learning it on this one state here. So I think you just want to share the logits on this. So I think then we just do like state.batch and like state.embed or something. Embed. That's not a full LSTM state though, hang on. You need to have a hidden into cell state for this. That's kind of awkward. You could use a GRU. Doesn't a GRU have one state? Yeah, GRU has one state, so you could technically do this. That might just be easier for now. And then you'll have to adjust these weights, but no big deal. Okay, so you get your action here. You still need log prob, don't you? Oh, you can just give it action. If action is none, else. Something like this. Okay. And then now you would still have to train it. You still have to train it. All this stuff works like before. Oh, you also have to add it to the optimizer. Like this. Okay. And then mu0 gives you what? Logits and value as well? 450. Logits and reward. 0. Logits. Reward. This gets batch.actions, which is good, and state.embed, right? Yeah, it gets the first embedding. So in order to give it state.embed should just be, hang on, batch time state.embed equals hidden 0. And then that should be That should be a dot detach, shouldn't it? Yeah, that should be dot detach. You don't want to train through that, I would hope. Maybe, we'll see. And then you just have this, right? Which is like move 0 actions. You don't need entropy for this thing. Do you not need entropy for this thing? Hang on, do you train this thing? You probably just train this thing to like match actions of original policy or something, right? Minimize error between actions predicted by the policy and the search policy. I'm trying to think how we want to train this thing. Kind of just the way that we are right now, right? Oh wait, does the policy even do anything in this setup? Because I don't know if the policy even does anything in this setup. There kind of is no other policy. Oh, wait, no, you're learning? Okay, I'm done. Hang on. I just have this thing in my head wrong. Yeah, it's not like an auxiliary thing. This is a replacement for the model. Okay. So, in this case, and they made it recurrent for a different reason, from what I was thinking of as well. Let me go back to drawing board here a little bit. This seems like it should be compatible, actually. This seems like this should be compatible. So like what they're saying here, right, is if you just have your policy that like takes in observation, right, and this thing is going to output action, they say, hey, why don't you just output reward and state, and then this can go, you take your reward and your action. Hang on. No, still not quite right. No, hang on, this is fine, right? So you need an obs encoder, right? So obs goes in here. Action goes in here, I guess. And then you get a reward and like value or whatever. And then they also want you to predict state. Well, this is a recurrent model, so this will just give you the next state, right? And then action goes in here. And this keeps rolling. So this works. So now I guess the thing that I'm getting hung up on here, right, is that they added recurrence here to implement their algorithm on top of a non-recurrent policy. So I need to now think of how this would work on top of a recurrent policy. Is it any different? I mean, the only thing that's wacko here is that the obs goes in here as the hidden state, right? But does that matter? Oh, it does matter because I need to be able to put obs in as well. Okay, shoot. I mean, I could technically do it this way for now. This would be an easier way to start. This would be a way easier way to start on this. And then it's not really recurrent in the same way. So you would still train it kind of like a recurrent net, though. You would kind of just you'd use a GRU. Can't put obs in at every step here. I don't think you can put obs in as the state like this. It'll mess up the way that you train an RNN. Like, obs needs to go in here. I think that's fine. This is fine. We just put obs in here. Obs concatenated with actions at least. Actually, this is kind of the simplest possible way to do it, right? Hang on. If I literally just... So this is your standard RNN, right? So you have S0, you have obs, you have actions. Right, and you have obs come in at every step. So I can put actions in here, that's no problem. This is T+1. And then all you do here, so you can like use this as a normal LSTM model, but then you can also use this during inference, maybe. I guess you have to train it on two different objectives, which is a little weird. But you could actually just take the output state here. Well, LSTM has two states. There's a hidden state and a cell state. So you could take like the extra state here and put it in as obs. I think that actually works. So then you save the, because the LSTM has two states, right? So you save one state of the two to just be arbitrary, whatever it wants to be. And the other one gets constrained that it has to represent the embedding of the obs, I guess. of the next obs. That's like possibly doable, I think. Is this insane, or is this like a pretty reasonable way to do something model-based-esque on top of an already existing recurrent model? Because this would let you just continue like rolling it out as well. Okay, let's try this and see how far we get before I get hung up on something else. So we don't need, I think we don't need the GRU or anything in this case then, do we? We just need to add, actions to the signature. This needs to predict. Oh, but this is real obs. Okay. It's a little tricky. Think we can do this though? The state gets that, produces everything that you need, and then this thing is going to output just going to output logits and value, right? Do you even need to predict anything else? It doesn't, right? So this can just stay as it was. Yeah, I see such a simpler way to do this now with this. Okay. We're going to stash or get stash buffer 0. Because I see a way better way how we can do it like this now. It's way easier. So action buffer. Okay. So now we have actions. State has this. Default will have action encoder. Cool. So now we have action encoder, then an encode observations. Okay, so this works. Use the restroom real quick, and then we keep implementing. Be right back. So we have this implemented now. all we should need to do is add this to train or state. It's literally in here already. Action equals batch.actions. I just haven't been using it. Okay. See if we can get this to train. The heck? Oh, I think you need to reshape the actions then as well, don't you? Yeah. So forward train needs to do actions. Oh, that's it though. It just needs a flatten. That's fine. Rid of my terminal. Okay, that actually does train. Seems. This should be like same or better perf than before as well because um, this is literally the same thing just with action embedding. So this is the first step. And then we'll add one auxiliary loss and see if it screws up training. And then literally from that, we should be able to have a model-based thing. That should literally be all it takes. This is not training anywhere near quickly enough, I think. I don't know what I could have possibly broken. Hang on, it's possible I hadn't checked the breakout config lately. What did I put in here? Should be fine, right? It's definitely not what we want. But here, let's do something. Okay, so this one does train. This one does not train anywhere near as well. These are the same configs. Okay, these must not be getting passed correctly then, because yeah, this works and the other one doesn't. So, bear with. Oh, there's an off by one, isn't there? There's an off by one. Okay. There we go. So that actually matters. It learns to condition quite heavily on that, it looks like. Oh, that's really good, isn't it? Hang on, that's better than we had before by a lot. Okay, maybe I've just been dumb not bothering making an action encoder. Because that actually looks like it really freaking helps, doesn't it? Holy. Yeah, okay, so at least we're gonna definitely guaranteed for sure get one good thing today, right? I'm pretty damn sure. We'll run a double check since this was so useful. Okay, there is some instability jank going on, it looks like, but we expect that's the experience buffer. Yeah, we expect that's the experience buffer bug. Oh, actually, interesting. Is it, no, this is more aggressive than before. Maybe it is the same. Same curve. Hmm. Well, that learns way faster than it used to, so something got better, but... Okay, action encoding doesn't actually help, it's just the whole thing must have gotten better, that's weird. Unless I didn't check out the branch or something. No, I'm on it. Okay, that's fine then. It would be kind of weird if it helped that much. But now we have this. We can do some stuff with this. Next thing is going to be additional loss on LSTM. Let me go remind myself which one of the states is which. It's the hidden state H that we need. So this needs to be in forward train. State dot. What format do we want it in? We probably want it in this format. Like this. And then LSTMH is going to have to be normed towards that. And that would be done right like here-ish maybe. It's not Neptune, this stuff. Do we not get LSTMH out of this? We should get LSTMH, right? Length 1. This needs to return full. We're gonna have a problem if this doesn't return us full data. No, it does. It returns the full thing. So why aren't we getting it? New value. Logits. Oh, that's layer. It's one layer. That's totally fine. Is that right? It's one... No, hang on. That doesn't make sense, right? Why is this 1? Oh, it only gives you the final hidden state. Shit. Wait, isn't this the one that we want anyways, though? If I just do, if I just train like a layer or two that projects... Just have to train something that projects this. Okay, that's not bad. Yeah, state dot. I just need state hidden, I guess, on this. And then this default policy needs like yeah, this needs like an extra loss on it. Just like small little net here. What's the dimension of this thing? Is it 64? I think 64 is the time, right? 64 is the time. This doesn't have to be recurrent, I guess. So next state predictions. State park. world loss, then okay, you have a world model in here. It seems like the loss is exploding, but you have it. Yeah, the loss is completely freaking exploding. Let's try 1. Technically, these don't have to be detached. Guess we try that next. Okay, well that fixes it, right? Now it is very good at predicting next state. Does it still train? A bit slower, but it does. Is it even slower? 30 mil for 800? Yeah, it's a bit slower. Not that much. And you get a good world model loss. So, let's commit this. Technically, you don't even need to have a network here, right? I think this probably messes it up, though. Seems not. Does it still train? Still trains perfectly well. Actually, let's log this one. I'm curious to see how this stacks up. Because now you're just saying that the output should be next state, right? And then it should be really, really easy from next state to predict, or encoding of next state, which should be very easy to predict reward from, because you can just see whether you broke a brick, I guess. Okay, I mean, that's basically the same curve. So this objective doesn't seem like it hurt anything. Did I do this right? Is it really this easy? I mean, I guess it wouldn't be that surprising. Like, predicting the next state, like, that is a good thing to predict generally, right? So I think we kind of just get world model for free then with this setup, right? Next state, unless I did something wrong here, but let's just make sure that these are different. I mean, they'd have to be different though, right? This off for Neptune. Yeah, these are different tensors. Okay. So, like technically, we can just do mu0 in the forward pass now, can't we? It's just use the world model to try to find better actions, right? Like we can do any sort of search that we want now, right? Isn't that's the whole point? Where's it? What are you implementing? Something that's pretty close to mu0. I'm just trying to see like what's the easiest way I can get some sort of world modeling based thing into Puffer where I can like crank up compute in order to get more sample efficiency or leave it at base and get like the same result that Puffer gets right now. So far, all I had to do was uh, I make the encoder action conditional, so it gets to see the action taken, which you need in order to predict next state, right? And then I just added a loss between the output of the recurrent cell, which is like your intermediate hidden state, and the embedding of the next state, both of which are differentiable. U0 should be strong on breakout. I'm just using this as like a trivial quick test env to make sure I don't break anything. Like, no, technically I could implement it all correctly and it would be the same. I just want to make sure I don't catastrophically fail on breakout as a result of what I'm doing. I have lots of other test envs. But theoretically, I mean, it should do a little better once you do the search component. Okay, so encode observations, encode actions, goes right here. It's usually like this, right? Obs embed, hidden. So this hidden is the world model target now, right? So can I not just like write a loop here? I should be able to just write a loop here. You need to select the action for this. This is the one tricky thing. You need to select the action for this. So you start with like orig, obs, embed, hidden. And then you do like obs embed equals orig, obs embed, this takes like obs embed LSTM state. You need a rig LSTM state as well, I believe. State. So the hidden cell, or is the cell is, which one of these is trained to be, it's the hidden that's trained to be the next prediction. So this can be obs embed. And I think the only thing that's missing here is the action prediction, right? Because then what we would do is we'd be able to figure out which of these we actually want to use if we had the reward prediction. Oh no, we also need the action sampling. Because oh, that's a little tricky. Yeah, I messed up the action embedding here. Because it's predicting right now, it's predicting the entire embedding. It needs to predict the embedding without the action component. Because then the idea here, right, is that you have to run, you run the decoder on this thing, right? Get out of here, bot. Time is it also? 10:26. So I'm going to go for breakfast/brunch soon. Let me get rid of this bot. All right. This is just going to be false for now. We'll think about this after. Okay, so you sample logits, you get your action, your log prob. And then the idea is that this needs to get combined with obs embedding, but I don't have that right yet, right? And then this will get used to select which hidden state you use. And actually what we should do is we should leave these as hidden in LSTM state. And I should just do 0. Zero hidden. We don't need the values for now. Technically we could. We actually technically could just bootstrap from this value. Logits. I think it's better though to just do well. Let me see if I can like hack something real quick that would like do, we would expect to kind of do something. You kind of need to know like the best delta V. I think it makes sense to just predict rewards, right? Plus bootstrap value maybe. I think it's just something like this, honestly, right? We have to train that value head. Hang on. I think that's like all there is to to like doing something mu zero. Like obviously that's not like the full MCTS, but that's decent. Um, that should do something maybe. Just do a bunch of trials. Oh, we still have to fix the action head. I think I'm gonna have to do that after breakfast. But let's add the reward loss real quick, because that can just go by right by the value loss. It's like super basic. You do actually have to output the reward though. Shoot. I guess I just add it to state or something. Yeah, I guess I just add it to state. State.rewards. And you predict. I have to do the same thing, right? Did you have to install a special version of Triton? No, I didn't. Hey, Spencer. I'm doing world model stuff today. I'm seeing if I can get us like anything crazy to work. I think it's worth a day. I can get you another box if you need to play with one though. Like I can get you access to one. I have one I'm probably not going to use today. I don't know what you're working on. Normal box works just fine. I see. Yep. Yeah, 5090 stuff's a pain in the ass. We're definitely going to make sure that we don't have that problem with 40 boxes when we order them. Well, maybe this does make sense to just put in the LSTM. Yep. I gotta, like, I'm hungry though. I gotta go get breakfast and stuff. And I will be back soon. I'm just gonna get some food real quick. And then we're gonna do this all day long. We're gonna see if we can get some world model based thing to do a thing in Puffer. Thanks folks for watching. If you're interested in this stuff, Puffer.ai for all the things. We are 2 stars off with this rounding up to 2K. So please just go ahead and star Puffer. Helps us out a lot. And you can join the Discord to get